There is another alternative way to find the value of inductor as well. So let's see what is that. Behind this point, at this point we have a rectifier, and after that rectifier we have used a inductive filter whose inductance is given by, whose impedance is given by this ZL, and this is my output load R. So if I ignore the part behind this impedance ZL, and the value of and at this point I know that the voltage, the output voltage of the rectifier was obtained at this point V, to which I had called V1 in my previous slides, and this is V1 or VL I can say. So this is VL is the VL or V1 is the voltage obtained at this point, and it is the output of the rectifier. The voltage waveform obtained at this point will have all these terms. It will have a DC value in it, and it will have some components of twice the frequency, and some component of 4 mega T, and some component of 6 mega T, and so on. What I want to do is I want to obtain only the DC output at this point. After passing through this inductor, from this inductor I want to obtain only DC part. I can say that the input to this inductor will be something like this. It will have different frequency components, and at the output I want to suppress all those frequency components and obtain a average output value, which will be DC. So for that I want to design an inductor that can suppress all these higher components. So I will first consider the second component. For Vm by 3 pi is equal to 666.67. So this value is basically, if I put the value of Vm, which was 1570, so the result is of this 4 into Vm divided by 3 pi, it comes out to be 666.67. This is basically the dominant component in my this waveform that I need to suppress. If you will calculate the value of this 4 by 15 pi, it will be very small, and similarly 4 by 35 pi into Vm will be further even more small. So I can ignore these higher components and only consider and focus on this first component, and somehow try to suppress this after passing from this inductance. So the transfer function of a scenario like this will be V ripple by V2 is equal to R over R plus J 2 omega L. This V ripple is basically the part of this. I want to suppress this value 666.67 volt, and after suppressing I want to ideally I want that the value after this should be completely blocked, but for that it is quite difficult and impossible. So this value after passing through, I want that it comes out to be 10 volt only. This ripple reduces to 10 volt. That was my design specifications. So V ripple by V2 is this value, the second component in this value. V ripple by V2 is equal to R over R plus J2 omega L and its magnitude. So by evaluating this expression, the value of inductance again comes out to be 21.99 Henry, which is same as I calculated using the previous method. So once again I will repeat what I have tried to do. I have tried to do that at the input of this inductor, the output waveform was like this, that is the output of the rectifier. It had many components that are represented by this equation. When I calculate the value of 4 Vm by 3 pi, it came out to be 666.67 volt, which is a dominant component. And if I calculate 4 Vm by 15 pi and 4 Vm by 35 pi, they are very small and can be ignored. So I will only focus on suppressing this this second component, and I have donated it by V2. So by its transfer function is V ripple is the voltage, is basically the voltage obtained at output after passing through this inductor. Okay, see that the DC value of that is also a part of this Fourier series will be obtained at output without any resistance. So the DC value 2 Vm by pi will pass from this unaffected, and this 4 Vm by 3 pi, this component will be suppressed by this inductance and will come out to be 10 volt. So this will be this AC component that will be overriding over this DC voltage. So the output voltage obtained will be something like this. And when we calculated its expression, the inductance came out to be 21.99 Henry, which was same as in case of the first method.